My name is Kevin Yee, and I am the chair of the Marketing Steering Group. I have the pleasure of being the moderator for this morning. Just as a reminder, as Derville has mentioned, we will have a Q&A session after the presentation, so please submit questions in the Q&A panel. With that said, it's my pleasure to introduce the first session for the workshops, which is how MAS simplifies the integration of cameras and displays in automotive architectures. We'll have the honor of 3 different speakers in this session. Ariel Lazary, which is the vice chair of the MIPI A-PHY working group. We have James Goel, who is the chair of the technical steering group, as well as the vice chair of the MIPI display working group. And then we have Hiro Takahashi, which is the lead for the MIPI camera service extension subgroup. So with that said, I will pass this over to Ariel.
Yeah, thank you, Kevin. And hello, everybody. My name is Ariel Lazary of Qualcomm. Today, I will start presenting an overview of the MIPI Automotive SerDes Solution, also called MAS. Then we'll hand over to Hiro, who will be providing a deeper dive of the MAS for camera and sensors. And finally, James will provide a deeper dive of MAS for displays before concluding and opening the floor for Q&A. So let's start with the MIPI Automotive SerDes Solution, also called MAS. So what it is all about. At first, let's have a look at A-PHY, which is the foundation of MAS. More detail will be presented later today by Ido and Raja. Today's camera, sensors, and display are using standard MIPI interfaces that are connected to the ECU by using proprietary SerDes bridges over the automotive long-reach channel. And this locks the OEM into a single SerDes bridge supplier. With A-PHY, in the first deployment stage, multiple vendors will be able to provide interoperable devices using a standard technology. And by that, lowering the cost through the standardization and the economy of scale. In a second deployment stage, A-PHY could be integrated directly into the sensors and into the display's T-con. And finally, A-PHY could also be integrated into the SoCs, and by that, eliminating the need for bridges and reduce the EBOM cost. Take an example, if you have 20 camera sensors and display in a car, one could eliminate up to 40 bridges, and that will be a significant saving. So MIPI A-PHY is the first industry standard long-reach asymmetric SerDes physical layer specification. It supports up to 15-meter coax or 10-meter STP or SPP cables, connecting the ECUs to sensors or to displays. The asymmetric link provides up to 16 gigabits per second on the downlink and 100 megabits per second for the uplink supporting the control channels. The A-PHY has been specified to withstand stringent automotive requirement with high noise immunity, featuring an ultra-low packet error rate, which is below 10 to the minus 19. The new version of A-PHY 1.1 is completed and is now currently in adoption process. It will add support for lowering the cost for legacy cables and connectors. It doubles the uplink speed to 200 megabits per second, and it provides support for star-quad cable, and by that doubling the downlink data rate up to 32 gigabits per second. So the A-PHY 1.0 has been adopted as IEEE standard 2977 in June. And by that, it expands the access to an automotive SerDes specification for non-MIPI members. For example, OEMs, cable and connector manufacturer, as well as other ecosystem stakeholder can benefit from that. And the next step will be to submit the A-PHY 1.1 for the adoption process of the IEEE. So MAS provides a framework for the end-to-end automotive SerDes solution, from the sensor to the ECU, and from the ECU to the displays. It includes the A-PHY, as well as the protocol for the sensors and the displays. And it supports both the bridged A-PHY and integrated A-PHY configuration. And the figure illustrating where we can find mass in the car. For example, in automotive ECUs such as ADAS or infotainment system, it can be also found in sensors or in display modules. We have a so-called mass guiding principle. We have three main elements for this guiding principle. The first element is the PHY, the A-PHY, which is the foundation of mass, featuring a high noise immunity PHY. The noise level has been determined after an extensive EMI and EMC measurement and test campaign. The second element are the protocols, leveraging and extending all the well-proven protocols that are already used in billions of devices and providing economy of scale and reducing the NRE cost. By providing the protocol adaptation layers for all the MIPI protocols, as well as for the VESA DisplayPort, and also for all these other supporting interfaces such as Ethernet, I2C, and GPIO. And the third element is the extending the protocol specification to provide end-to-end functional safety and security. The end-to-end at the application level, from the source to the sink, not only from bridge to bridge. And we have a free extension specification, the CSE for the camera service extension, the DSE for the display service extension, and the MIPI security specification. Here are more detailed features of mass solution element. So the first one, we talk about the PHY, a very robust long-reach PHY with packet error rate of 10 to the minus 19. So what does it mean? It translates into a mean time between failure of a single error over the full vehicle lifespan. It provides a bounded low latency, which is below 6 microseconds at Gear 5, and provides a high-speed downlink to support aggregation of multiple 4K camera and display over a single cable. The second is the application level end-to-end functional safety and security, covering various topologies and providing the flexibility and trade-offs coverage for verification per frame, per RY, per message, with compression enabled or disabled. It provides high-level diagnostic coverage to meet the required safety goals. And the end-to-end security is providing authentication, data integrity, optional encryption. And for premium content protection, MAS provides support for HDCP for display. And the other element is the deep system level consideration for native interfaces and the legacy ecosystem, enabling support for heterogeneous display protocol, for example, DSI and DisplayPort, and also enabling different source and sink configuration like SEPs on one side and D-PHY on the other side, or with bridge or without bridges. Here are two examples of supported topology for which MAS provide an end-to-end protection. On the left side, you can see an example of camera and sensor aggregation. There is an end-to-end protection on each path from the sensor to the ECU through the aggregator bridge. On the right-hand side, you can see an example of a single ECU driving multiple displays in a daisy chain. The three display streams are carried all together on the first link. Then, each display stream is individually end-to-end protected from the ECU source to the destination display. So, here's the protocol stack diagram for MAS. At the base, we have the A-PHY that provides a common PHY and data link layer to all the protocols. Then, each protocol has a specific protocol adaptation layer, or PAL. There is one stack for the camera, one stack for the MIPI display DSI2, and one stack for the VESA DisplayPort. And each of these stacks have a service extension layer above the protocol, directly at the application, where the source data are produced and where the data are consumed. That is to provide the end-to-end protection. So with CSE to provide functional safety and security for camera, the DSC to provide functional safety, security, and HDCP for display. And with that, we have also the MIPI security specification that defines the framework for mass security applying to all of the stacks. Most of the specification have been already released or are in the adoption process now. And the current effort in MIPI for mass are now focused on adding the security. So mass is using the 1 to 5 model to identify 5 typical components in an A-PHY network, connecting the number 1 controller or SoC to the number 5, which is the target peripheral device, such as a sensor or a display. The number 1 controller can be either the data source for the display, or it can be the data sink for the sensor data. And it may have a native PHY interface, such as C-PHY, D-PHY, or DisplayPort PHY, or it can have a A-PHY interface for long-range automotive. Then the target, number 5, can be a CSI2 sensor, a display, TDIC, or a TCON controller with either a native PHY or A-PHY. The model supports also optional A-PHY bridges for number 2 controller side bridge and number 4, which is the target side bridge, which are used for converting between the native protocol PHY and the A-PHY. The number 3 is the A-PHY forwarding element, and this component is optional. It is used to route A-PHY packets through the A-PHY network, for example, when using daisy chain devices. So end-to-end protection is provided inbound with a SEP, service extension packet, for CSI2, DSI2, DisplayPort, and EDP. And for sideband protection, we are using the ESS CCI protocol, and Hiro will explain later, for CCI and A-PHY control. And this end-to-end model can be applied directly from the controller to the target over any MIPI PHY. Yeah. And by that, I will hand over to Hiro to provide an overview for mass for camera and sensor.
I'm Hiro Takahashi, lead of Camera Service Extension Subgroup. In this session, I'll introduce mass for camera and sensors. Okay, let me start from CSE, Camera Service Extension. CSE enhances CSI2 with end-to-end functional safety and other features. It adds some extended features to CSI2 for next-generation image sensor applications. CSE, the upper layer of CSI2, is used not only for mobile and IoT applications, but also for mobile applications. There are 3 key features in CSE spec. First, it supports end-to-end functional safety, and it has 2 blocks, CSE-I, image data transfer, and CSE-C, control data transfer. To meet the requirement of the functional safety, CSI uses SEP format, and CSE-C uses ESS CCI. The other 2 features are that it expands the number of data type defined in CSI2 and expands the number of virtual channel defined in CSI2 as well. As a future enhancement, end-to-end security will be supported by CSE version 2.0. Now, let me explain end-to-end functional safety in more detail. This is the overview of camera system. As you can see, there are 3 types of image sensor and SoC. First, integrated image sensor SoC. A-PHY is implemented in the image sensor SoC. Second, while A-PHY is not implemented in the image sensor SoC and CSE is. The third, legacy CSI to image sensor SoC. Neither A-PHY nor CSE is implemented in the image sensor SoC. In this system, end-to-end functional safety is available for all combinations, but the meaning differs depends on the type it belongs to. In the integrated image sensor SoC, end-to-end functional safety means the protection between image sensor and SoC. To meet the requirement of end-to-end functional safety, CSEI provides SEPDT and CSEC provides ESSCCI. In the non-integrated image sensor SoC, the range of end-to-end functional safety is the same as the integrated devices. To meet the requirement of functional safety, CSEI provides SEPDT over CDFI, and CSEC provides ESSCCI. In the legacy CSI to image sensor and SoC, the range of end-to-end functional safety differs from others. If both serializer and deserializer support legacy mode conversion and ESSCCI, end-to-end protection indicates that between serializer and deserializer. Then let's turn to CSEI and CSEC. Okay. CSEI provides 3 SEPDT packets. SEPDT packet over A-PHY, D-PHY, and C-PHY. These packets are different, but share the same structures, SEP, Service Extensions Packet. And SEP has CRC and message counter for end-to-end functional safety. It consists 3 parts: extended packet header, payload data, and extended packet footer. Here is the example of the integrated image sensor. In this case, CSEI provides SEPDT packet over A-PHY. It has the same format as the SEP. Message counter and CRC in this SEPDT are inserted for end-to-end protection between SoC because SoC verifies these message counter and CRC. In the PAR CSI2 layer, an SEPDT packet over A-PHY is divided into multiple chunks. In the A-PHY layer, each chunk shall be encapsulated in a single A packet. Message counter and CRC in this A packet are not inserted for end-to-end protection because these message counter CRC are consumed by A-PHY layer. This is the example of end-to-end functional safety for CSEI. End-to-end protection can be supported regardless of the type of PHY, from a starting point to a destination, because SEP is PHY agnostic. And SEP is generated by CSEI in image sensor. The content of SEP doesn't change because the SEP is tunneled via the transport channel, such as D-PHY, A-PHY, and C-PHY. So CSE provides end-to-end functional safety across the interconnected network using SEP. Okay. Let's move on to CSEC. CSE for control data transfer. CSEC provides the ESSCCI, Enhanced Safety and Security Camera Control Interface. CCI read and write messages are extended with ESSCCI tags, including message counter and CRC. There are 2 modes in ESSCCI, Mode 1 and Mode 2. The ESC-CCI controller and the target devices shall always support both ESC-CCI Mode 1 and Mode 2. In the ESC-CCI Mode 1, ESC-CCI tags are transmitted along with the CCI message. Each message can be verified and processed as soon as it's received by target or by the controller. In the ESC-CCI Mode 2, ESC-CCI tags are accumulated over multiple messages. The accumulated tags are sent as CSI2 embedded data from the target to the controller. Here, you can see the transaction of ESC-CCI Mode 1. The ESC-CCI tags shall be added after CCI-I2C read-write messages as a footer in Mode 1. In both read and write transaction, the basic structure is the same as the existing CCI, defined in CCI2. The updating point is that ESC-CCI tags are inserted at the end of the transaction. Both message counter and CRC are included in the ESC-CCI tags in order to meet the requirement of end-to-end functional safety. Okay, that's all from me about CSE. So let me hand it over to James, who is to talk about the display.
Morning, everyone. This is James Goel. Thank you, Hiro. Thank you very much for that, a very informative section. I'm James Goel, Vice Chair of the Display Working Group, and today I'll be talking about MAS for automotive displays. I'd like to start with this application that illustrates how MAS end-to-end functional safety and in the future security will be implemented both for some camera, as Hiro just described, but mostly for the display side. In this application, the traditional side mirror has been replaced by a new camera sensor that has wide-angle view, night vision, and is low profile to improve aerodynamics and economy of the car, which is very important in electric vehicles. In this application, the camera is reading the side of the car, and you can see that the ECU has started processing the images to provide this safety information in terms of these safety icons. This entire end-to-end application, given the risk profile, has been determined in this use case to be ASIL D level and requires a very severe and a high functional safety and in the future security. So let's walk through how MAS can provide the solution for this. Here we have the camera, radar, lidar in the back of the car, or in my other use case, it was on the side mirror. And what happens is MAS is based on MIPI A-PHY. These icons indicate functional safety and security. Protocols are added, as Hiro just described, to the camera sensor. The A-PHY backbone brings it to the ECU using these functional safety and security protocols. The automotive ECU does its image processing and then generates for the display the graphics with continued addition of new functional safety and security protocols so that you have a smooth transfer between the camera and display over the A-PHY to the final display of the car so that the user can actually see it. And the display protocol supported will, of course, be DSI2 from MIPI and VISA, embedded DisplayPort, and DisplayPort. There we go. Now we're going to talk about two different topologies. In this block diagram, it explains how MAS functional safety and security can be done in two different ways. This top diagram shows a bridge-to-bridge MAS solution that is best suited for existing legacy ECUs and displays. So in this case, This is a legacy ECU display generator and an existing display legacy DSI2 display. In the bottom, I've just selected a different topology where you have the same graphics processor and you can have EDP or DP in the bottom. In this top display, the protocols for functional safety and security apply only to the A-PHY bridge solution. So in this first legacy use case, these do not have the new updated MIPI protocols, but you can still take advantage, at least from the bridge to bridge, using the new protocols for a SEP and other things that we'll talk about in the rest of the presentation. So this means you can immediately start using A-PHY SerDes today with link-to-link or bridge-to-bridge functional safety and security. However, as things get integrated or as new display processors and new sync displays come online, you can incorporate the MIPI functional safety and security protocols directly into the display engine and directly into the display itself. The benefit of this, of course, is that it gives you end-to-end functional safety and security all the way from when the pixel came through the camera, all the way through the graphics processor to the final display. And we tend to call this a kind of a glass-to-glass, end-to-end functional safety solution. Let's dive into this a little bit more detail. So this diagram shows more of the detail about what that bridge-to-bridge solution would look like. Here you have a traditional legacy ECU. In this, the GPU or display source generator talks to the DSI2 protocol generator, and it transmits the pixel data across the native C-PHY or D-PHY interface. The bottom shows a VISA DisplayPort or embedded DisplayPort example using legacy applications where there is no existing or new functional safety or security protocol. In this case, the native protocol gets translated in the bridge chip. So this is an A-PHY transmitter bridge. Both of these are A-PHY bridges. There is a new MIPI protocol called the DSI2 adaptation layer, and this is defined in the DSE 1.0 specification. So this is the PAL for DSI2. Here you have VISA embedded DisplayPort protocol adaptation layer that's also specified. So you can see legacy applications can just plug directly using their native interface into the bridges, and these protocol adaptation layers provide the end-to-end or bridge-to-bridge functional safety and security. Now in this application, in this diagram, we have gone to the next level, integrated the protocol directly into the new upgraded ECU processor, and of course the display would have the same. So you can see here on the same, the display also now has the adaptation layer protocol, and you can directly drive the A-PHY physical link-to-link end-to-end to make sure that all of the protocol from the very generation here at the GPU all the way to the display is covered with functional safety and security. Same can be said for VISA DisplayPort using the adaptation layer protocol end-to-end with embedded A-PHY. Now, when we were designing the DSE specification, we wanted to make sure that it met the world standard ISO 26262-5 Annex D, and specifically there's a table in Annex D that talks about the communication bus safety mechanisms. The last 4 particular rows in this table talk about information redundancy, frame counter, timeout monitoring, and combination of information redundancy and these other use cases to give you high robustness and high functional safety. So we took this as one of the key requirements for our functional safety and specification and protocol adaptation. And this is how we've applied it. The MIPI DSE service extension specification defines a new packet type that implements the safety mechanisms described in that previous slide, which was table D6 in Annex D. These service extension packets, which are shown here, are calculated during the pixel to byte conversion of the DSI2 or EDP protocol encoding. This figure illustrates how a SEP header here and footer here begin and end at the start of each blanking and active line in the video defined by the DSI2 long packets. SEP header and footer packets also protect the command and control interface for DSI2, but it's not illustrated here. The MIPI protocol adaptation layer for DSI2 and EDP define the SEP requirements and how they are used to protect the long packets and short packets sent from the A-frame and source bridge to the A-frame receive bridge. So let's dive into that in a little bit more detail. This figure illustrates how the SEP header is able to encapsulate a traditional DSI2 long packet payload. You can see here the DSI2 long packet and SEP header is used as the payload to calculate the SEP header CRC32 value located here and in the footer. So you have a combination of header and footer information that protects this SEP payload. The same is also possible. This is a long packet up here. The same protection is also afforded to the DSI2 short packet, so that both long packet and short packet are protected. For details on the DisplayPort, please see the adaptation layer for DisplayPort, where these details are described specific for VESA. This diagram illustrates how exactly the display service extension and SEP protocol header and footer are formatted. Here you can see the extended data type in the first 32 bits defines how the SEP is to be described. It has specific extended data types to describe different types of SEP payloads. The DSE specification currently supports DSI2 and VESA embedded DisplayPort, but there are many other data types that are also protected by SEP. These second 32 bits include a message counter, a 16-bit message counter, and you can see there's also provisions for HDCP structures. And finally, in the footer, there are provisions for CRC32 to protect the entire SEP payload. And in the future, you can imagine this gets expanded to include security, as Rick will talk about later. Timeout monitoring can be implemented by tracking the SEP message payload and the SEP counter length to ensure that there are no frozen frames and that there is consistency between the SEP counter as it's transmitted through the end-to-end protocol. For more details, please see the DSE 1.0 specification. Finally, I will just very briefly go through this diagram. You can go from the source to the sync display, and please note and read the specification. You can see how the source payload pixels are protected from the source display through the A-PHY bridge, finally to the sync display. And with that, that's the end of my presentation. Thank you very much for listening. And Kevin, I pass it back to you.
Well, thank you very much, James, Hiro, and Ariel, for sharing with us about how MAS simplifies the integration of camera and displays into automotive architecture. I would just like to remind everyone that if you have questions, please feel free to enter them into the Q&A panel. We have a few minutes, about a little less than 10 minutes, and we will address whatever questions we can and follow up with them. Let me check. Let's say the first question we have for the panel to answer is, speaking of MAS, do I have to implement MAS as a whole solution, or can I pick and choose different components of MAS?
So maybe RL, you can start and I can add some commentary here.
Yeah, I can take it. Let me just scroll up. You don't need to have all the MAS specification to implement a specific application. Let's say you just have a camera then you need only the specification which are related to the camera. So if your device is supporting CCS, you will implement CCS, but you don't have to. What all the applications have, they all have the A-PHY with the physical layer and the data link layer, which is the A-PHY. Then if you're in a camera case, you will implement only the protocol adaptation layer for CSI2, and probably you will implement also the protocol adaptation layer for I2C for to enable the camera command interface. And maybe if you need, you can also implement a GPIO adaptation layer, because some camera module may need some GPIO, but you will not need to implement, for example, SPI or Ethernet or VESA DisplayPort or MIPI DSI. You just need to implement the stack that is related to your device. The service extension is also required if you want to enable end-to-end functional safety and security, which is highly recommended for automotive application. Is that answering your question?
Yes. Any other comments from James or Hiro?
My only comment on display is that you do need to implement a source and end protocol. So yes, it is exactly correct. You can implement only part of the stack or functional safety using SEP bridge to bridge to, if you want to support legacy solutions for display only, but you must always implement a source and an end solution. And that ensures that at least that particular part of your topology is protected. Hiru, any comments?
Nothing from me.
Great. Thank you, Kevin. That's the answer.
Okay. Another question we have is with the adaptation layers, there's a question of, does it matter where the adaptation layer is implemented, in the sensor or in the SerDes?
So I could take that for the display side because I talked about that in some detail. The adaptation layer can be implemented wherever you would like to convert to A-PHY format. So in this first DSE version, the adaptation layer must be very close to the SerDes. So does that mean that it has to be directly in the SerDes? No. You could put the adaptation layer, as I showed in one of my diagrams, directly into a next generation a display or source, but then you must be sure that your SerDes is, your A-PHY SerDes is close by, because the output of the adaptation layer are A-frame packets, and those A-frame packets must go across an A-PHY. So hopefully that helps you. Where the SerDes is doesn't matter. The output of the protocol adaptation layer is always A-frame packets. Thank you. Any comment, Ariel or Hiru?
No, nothing to add. Thank you.
Great. Thank you, Kevin.
Okay, we have one additional question here. Hopefully we might be able to get two in, is, and this might be cheating into the other sessions, but the question was, when will MIPI finalize the security for camera, lidar, radar, and display? Is there a draft version to be shared at this time?
I can take that, and of course, Rick will talk in detail. We're hoping to have this ready by 2022. That, I'm the TSG chair, and that's the roadmap we have outlooked. So hopefully there's definitely draft things as MIPI members. Please come if you are a full MIPI member and the proper rate. I forget whether it's a contributor, a member, but definitely Rick has given many talks on security. And there's a lot of drafts that are coming now. So please come and join us. Kevin, any comment on that? I definitely was shooting for 2022, next year.
Yes, and I would encourage, as James had mentioned, there is a whole session on security that Rick will be speaking on, and I think he'll get into a lot more details on what's being done on the security side. We have 2 minutes left. One last question is, what is the encryption algorithm defined by CSE, if any?
Yeah, the one thing we can say though is questions goes out to Tim. We have worked very hard to use standardized public algorithms. We did not reinvent. We use AES and we use very standardized hashing functions. But the foundation is a DMTF SPDM, if you're familiar with those specifications. But we didn't invent new protocols. We used world standard and very reliable encryption. But yeah, please join Rick's security topics later today.
And with that, I thank the panel again. I think we're out of time for the Q&A. Any additional questions that you put in, we will respond to you. So please continue to ask any questions and answers. But I'd just like to thank Ariel, Hiro, and James again for their session. Thank you very much.
All right. Thank you, everyone, and have a great automotive session. Take care. Bye-bye.
Thank you for my side as well.